Suppose R is a partial order on A and S is a partial order on B. Define a new relation T on A times B as follows. T is going to consist of all the ordered pairs of, each coordinate is going to be an ordered pair from A times B. And those ordered pairs will be related if their first coordinates are related by R and their second coordinates are related by S. Show that T is a partial order on A times B. And then after that, we'll ask if R and S are total orders, will T also be a total order? Okay, well, let's just try and get a better sense for what this T is, what it means. And for that, let me just draw an A times B down here somewhere. So that'll be represented by some rectangle where this horizontal axis here is the A and the vertical one is the B. And okay, each point in here is an ordered pair in A times B. Now, they're going to be related if, for example, we have a point A, B. I should put the B here. Okay. And then another point, A prime, B prime. Then suppose that A just has sort of the standard less than or equal to total order, so that things on the left are smaller than things on the right. Well, then you see that here A is related to A prime by whatever relation that is. We're calling it R. And B is related to B prime if we assume that S is also that nice sort of total order on this axis. And so this point AB here is related under T to this point A prime B prime. Okay. Basically, it just has to do with the fact that to get from AB to A prime B prime, you have to go up and to the right. Okay, so that's sort of what T looks like. That's what it means for these to be related in T. Let's work out the logic. It'll take a little while, but it's good practice. So we know that R is a partial order on A and S on B. We want to prove T is a partial order on A times B. Now that means that R, first of all, is a relation on A, and it's reflexive, transitive, and antisymmetric. Same thing for S. S is a relation on B, which has those three properties. And same thing for T. All right, T is a relation on A times B. All right. Well, we can take care of our first goal very easily because T equals a set of points, all of which are in A times B times A times B. So that immediately proves that T is a subset of that set. So we just have these three properties to check. Let's take the reflexive first. And for that, I'm going to bring down our givens that R and S are reflexive. All right, so we'll write down the definitions of those and of T being reflexive. And remember, T is a relation from A times B to itself. So I want to show that for every element of A times B, which I'll represent as an ordered pair AB, that AB is related to itself under T. Okay, so we have a universal statement to prove, so we can assume, we can let AB be an arbitrary element of A times B. We have our new goal. And then we should look at the definition of T to figure out what it means for these to be related. And here it is, right? The elementhood test is that the first coordinates have to be related by R and the second coordinates have to be related by S. So we want to prove that A are A and B S B. And well, the fact that AB is in that Cartesian product means that A is in A and B is in B. And then that's going to allow us to do a couple universal instantiations, right? A and A allows us to write down this one, that A is related to A by R, and the other one gives us BSB. And we're good because that was our goal. So I just have the proof here for us to sort of look at, but let's at least see how we got this first bit. So first, we noted by the definition of T, that was what I said in the beginning, that this gave us our first goal. Okay, and second, we proved T is reflexive, so we were going to bring that one down here and worry about the other two later. And so we let A, B, B, an arbitrary element of A times B. We're going to show this. And then we said, because, well, that gave us that. Probably don't need to write that in the proof. And then these being reflexive, via their definition and universal instantiation gave us these two statements, right? So that's what I'll mention here, because R and S are reflexive, A are A and B S P, and therefore those two things together give us what we want, right? By definition of T, A, B is related to itself under T. So we have that T is reflexive. Let's take the transitive one next. So I'm going to use that R and S are transitive to prove this. And we remember the definitions there. We have, for example, A prime, A double prime, and A, such that the first is related to the second, and the second is related to the third, then the first is related to the third. And same thing in B. And I want to prove that this is true in T, so I get a big mess. Now I have to take 3 ordered pairs in A times B. And again, if the first is related to the second and the second to the third, then the first is related to the third, this time under T. Okay, so I have a universal quantifier here. So I can, in fact, I have 3 of them, right? I sort of abbreviated them all into one just to save some space. So when I can let those 3 ordered pairs be arbitrary elements of A times B. And then I can do direct proof to bring this antecedent over, and I'm left with just the consequent as my new goal. And we'll bring down our other givens. And, well, by definition of T again, which I've kept at the top here, this means that the first coordinates are related by R, and the second coordinates are related by S, excuse me. And so how are we going to come up with those goals? Well, the fact that all these ordered pairs are in A times B, we can sort of separate that out eventually and say that, well, all the first coordinates are in A, all the second coordinates are in B. And that matches up nicely with our quantifiers up here, right? We can do some universal instantiation now to, pardon me, before we do that, let's also break this up using the definition of T. So A, B, T, A prime, B prime breaks up into these 2 statements, and this statement becomes these 2. And I see. Then I'm gonna I'm gonna rearrange things a little bit, bring the R statements together and then the S ones together. And I can do that because I have a bunch of ands here, right? A bunch of conjunctions. So the parentheses and the order don't matter. And now I'll do some instantiations. So I get basically these conditionals brought down, and those conditionals are just what I can match with these statements here via modus ponens, right? So that one is going to give us our ARA double prime, and that modus ponens will give us our BS B double prime, and together those were what we needed. So let's think about how to write that. We're going to prove that T is transitive. And so our first step was to let all these guys be, I should probably include that, be arbitrary elements of A times B. And moreover, to suppose that this conjunction was true, which left us with that goal. And then we wanted to get all these statements somehow, and that just came from taking these T statements and breaking them up into R and S statements, and then reordering some things to get these 2, right? And okay, so I've just sort of listed all 4 of those statements here. And well, because R and S are transitive, and that's what gave us these universal statements, which eventually lost their quantifiers, right? And then via modus ponens gave us this stuff, okay? So somehow, because R and S are transitive, and because of what we just wrote in the previous line of our proof, We can combine the R statements to get AR A double prime, and similarly for the S statements for BS B double prime. And those guys gave us what we wanted for AB to be related to A double prime B double prime by T. All right, we're hanging in there. Now we just got one last part of the proof. Fourth, we proved that T is antisymmetric. And again, we're going to use that R and S are antisymmetric for that. So here are the definitions. For example, for all A and A prime in the set A, if A is related to A prime and A prime is related to A, then they must have been equal. Okay. And then same thing for T, but with ordered pairs instead of elements. And all right, this is going to look quite a bit like the previous step, the previous part. We will let these two ordered pairs be arbitrary elements of A times B, and then we'll do direct proof to bring our antecedent down. And then for two ordered pairs to be equal, well, we know that that just means their first coordinates are equal and their second coordinates are equal. And then we can use the definition of T to break these statements down like we have in the past. And we can do universal instantiation there using, and I'm skipping a little step here, that, okay, A and A prime are in A, therefore I have what I need to be able to write down this conditional. Okay, and similarly for B and B prime being in capital B. And now, okay, just put those on separate lines over on our goal side. Do some rearranging to bring the R's together, and oh, I have a typo there. That should be BS B prime. All right. And then we can do some modus ponens to get that A equals A prime from those two, and from the S's we get that B equals B prime. So we say, fourth, we prove T is antisymmetric. Let these two ordered pairs be arbitrary elements of A times B. Suppose that we have this conjunction, and we're going to show that those ordered pairs are equal. And all right, again, by definition of T, we know all four of these. Where are we? Down here? Okay, and then because, after some regrouping, because R and S are antisymmetric, we got these conditionals, and modus ponens combined with what we wrote in the previous line of our proof gave us these two equations, right? Because R and S are antisymmetric, together with what we wrote up here. For example, this one and this one gives us the A equals A prime, and the other two give us B equals B prime. And that's what it means for those two ordered pairs to be the same. Therefore, AB equals A prime B prime, which was our goal. So we're done with this part of the problem. We still had the other question, which maybe I should go all the way back up so we can see it. Beginning. It said if R and S are total orders, will T also have to be a total order? And it turns out that's not the case. Okay. And one way of saying that, in terms of the picture I drew here, would be if you have 2 points, you don't always have one that's both above and to the right of the other point, right? For example, in a much simpler situation that I've written out here for my counterexample, we could just let A be the 2-point set 1, 2, and same thing for B, 1, 2. Okay, that's a 2. And then the Cartesian product of A and B is going to be this 4-point set, right? That is my A times B. And okay, I'm going to take just the nice total order on both A and on B that basically less than or equal to. Okay, so 1's related to itself, 2's related to itself, and 1 is related to 2. Same thing up here. So I have that nice total order on each of them. And okay, so the T in this case is going to be a relation on A times B on this 4-point set. But you'll notice that if you look at these 2 points right here and here, right, 1, 2 and 2, 1, neither of those are related to each other, right? Because neither is above and to the right of the other. Right, so in order for this to be true, you would, in particular, looking at the second coordinates, you would need to have 2s1, right? But 2, 1 is not in s, and for the other order, you would need 2r1 from the first coordinates, but the ordered pair 2, 1 is not in r, okay? So that is why, even though we do have sort of a total order on each axis, we do not have a total order on all the ordered pairs in their Cartesian product. All right, that does it.